Okay, area between the curves, which is section 6.1 in your book, is actually a relatively straightforward section. It only has to do, there's only a couple of wrinkles that separate it from area under the curve, which we have done up to this point rather successfully, and which you should have down. It should be, relatively close to second nature by now. Now, obviously, if you have something like this, right, and this is f of x, and we're looking for the area between a and b, obviously the area is, from a to b of f of x dx, right? Well, if I'm looking for the area of g of x from that same a to b, and I know that the area under g of x is going to be a to b of g of x dx. Now, let's see if I can actually recreate those so that they look something like they previously did. So if we have f of x and g of x, right? And let's just pretend that those are the same. I'm not an artist, and I don't have as steady a hand as an artist does. So let's just pretend that this is the same f as previous, okay? And of course, this g is the same. Now, if I want to find the area between the curves from a to b, it stands to reason that I would take the larger area, f of x, right? And then I would just subtract the smaller area, and of course that would give me the difference. But I can just as easily actually do it like this. Okay? Because you got to remember that when you're actually doing this, you're looking for cross sections, right? And you're looking for cross sections of a particular width of a particular height, okay? Well, the width right here is dx, or delta x, and of course your height right here is simply the top, or the more positive, minus the bottom, or the more negative. And so we have height times width of the infinite number of infinitesimal cross sections from A to B, and therefore we have height times width accumulated from A to B. Okay? And so basically, if you're doing it, with respect to the x-axis, it's the top minus the bottom. The reason I said more positive minus the more negative is because eventually we're going to be doing it with respect to the y-axis as well. So that's something to look forward to. Okay, well, let's go ahead and I'm going to go ahead and show you the wrinkle real quick, and then we're gonna do a couple straightforward examples before we get to it. The only thing you have to be careful about is if you have f of x and you have g of x, and they don't stay in the same relationship on your interval. Okay, notice that this one right here is on the bottom, and then it's on the top, okay? And notice that this one right here, where is that green? This one right here is on top, and then it's on the bottom, okay? So I would basically have to figure out where the intersection is. Okay, where is that intersection? And then I would have to actually set up two integrals. One from a to c, where f minus g represents the height. And then one from c to b, where g of x is on top, and therefore g of x minus f of x represents the height. Now, some of you who are really, really clever are thinking to yourself, why waste that time? I'm just going to go ahead and slap absolute value around that bad boy and just proceed from there. And on your calculator, even if it was a calculator one and not one that you actually did by hand, on your calculator you can actually do that. And you'll actually get the right answer. It'll churn it out and the algorithm will work and everything will be hunky-dory. Until such time as you get to AP exam, and the AP exam specifically forbids you to use absolute value on a particular problem, and you're used to using the shortcut absolute value method, and now you actually have to work it out. Okay, that's going to be a problem. So we're not going to do any of them by absolute value. I'm going to show you how to figure it out the long way, and it should be relatively straightforward for us based upon what I've led you through the last couple of years. So let's go ahead and get to some examples. Alrighty, let's say that I am given f of x is equal to x squared plus 2x plus 1. And let's say I'm given g of x is equal to 2x plus 5. Okay? Well, you should recognize the fact that that's x plus 1 squared. But you got to remember that what I need to do first, since I'm just given two of these equations and I'm not given limits of integration, it stands to reason that the limits of integration are implied by the two functions, and they are, meaning that your limits of integration are going to be determined by where these two functions meet. And therefore I have to basically say, well, when is x squared plus 2x plus 1 equal to 2x plus 5? Well, notice that the 2x's go bye-bye, and if I subtract 5 from both sides, I'm going to get x squared minus 4. That should be relatively straightforward. It winds up being x is equal to plus or minus 2. So I know that my limits of integration are going to be plus or minus 2. Now, that means that in order to figure out the area between the curves, I know my limits of integration. Now I just need to figure out which one is more positive on that interval. Well, first of all, we can reason it out, okay? This is an upward-facing parabola. If an upward-facing parabola intersects a linear at 2 points, there's only one possible shape that it can have. It's going to look like that. And that means that we're looking for that area right there. And on the interval, the linear, and in this case that one's g of x, the linear is the more positive. So we see the fact that from just reasoning it out graphically, that it should be that. Now, if you didn't reason it out graphically, could you reason it out another way? Well, yes. If the two functions only intersect twice, that means on the interval between them, they're going to have the same relationship. Meaning f of x between -2 to 2 is always going to be above g of x, or it's always going to be below g of x. It's not going to change. Because if it changed between -2 and 2, you would have found another point of intersection. But since you only found 2 points of intersection, you know that on that interval either f of x is always greater or g of x is always greater. So could I actually take a representative value, a representative x value, within that interval and just plug it into both? Sure, and the easiest one on that interval is 0. Plug 0 into here and I'm going to get 5. Plug 0 into here and I'm going to get 1. Because that representative point, because that point is representative, or the outputs at that particular value are representative of what happens on the entire interval, 5 is greater than 1, so I know on -2 to 2, g of x is greater than f of x. Okay? Which means, now that I have this, all I have to do is very quickly simplify, and I know that once I break down those parentheses, that's going to be negative, that's going to be negative, okay? And therefore the 2x's and the -2x go bye-bye, and I wind up with 4 minus x squared dx. Now, that shouldn't surprise us that it's 4 minus x squared and this is x squared minus 4. Because if these two are on opposite sides of, If these two are on opposite sides of the equal sign, then simple subtraction gets them both on the same side, okay? So we know it's either going to be x squared minus 4 or 4 minus x squared, and since g of x comes first, it's 4 minus x squared. And we get 4x minus x cubed over 3, and we're going to evaluate it from negative 2 to 2. Okay? Now, I could have shortcutted this, and I'll discuss that in just a second. But from here, it winds up being 8 minus 8/3 minus negative 8 minus negative 8/3. Well, gosh, if I just distribute that negative, it winds up doubling that, right? Well, 8 is 24/3. So 24/3 minus 8/3 is 16/3. 16/3 plus 16/3 is 32/3. And that is the answer, okay? Let's go ahead and see what that looks like on the graph, okay? I've plugged in, you plugged in x squared plus 1 and 2x plus 5. And let's go ahead and graph it. And we see, in fact, that it is the x plus 1 squared, and we should know what that looks like because we spent, hours and hours and hours doing transformations. We see as it comes through the fact that it actually looks like it does intersect at negative 2 and then again at 2, okay? And we see that on the entire interval, the linear is indeed the larger one, okay? Now, what happens here is that the moment that I've simplified this integrand into 4 minus x squared, does this 4 minus x squared know where it came from? No, the 4 minus x squared is just 4 minus x squared. It's an intermediate step, but it doesn't know that it came from here. But let's just think about the graph of what 4 minus x squared looks like. 4 minus x squared is symmetric about the y-axis. And if it's symmetric about the y-axis, and the limits of integration are as well, I could have shortcutted this by multiplying it by 2 and running the limits of integration from 0 to 2 of 4 minus x squared dx. And that, of course, would have made things just a little bit easier. And what I mean by easier is, it cuts out the possibility of losing a negative and making that careless error. So you have 8 minus 8/3, and of course that's minus 0 minus 0/3. That's meaningless. And what we get here is exactly what we reasoned out up here. It's 16/3 times 2, or 32/3. Now, of course, that was one example, and it took a really, really long time to actually pull that one off, especially in light of the fact that I was trying to do some explanation to lead us to that first example. Let's do a second example real quick, and let's actually get through it pretty quickly. We see that if we're given, and I'm going to keep using f and g, it doesn't really matter. You could use, the textbook that I'm pulling these from is using y1 and y2, but it doesn't really matter. They mean the same thing, obviously, but I'm just used to doing it. I just like function notation a little bit better than I like fiddling with y. Now, obviously, this is an upward-facing parabola. This is a downward-facing parabola. If I'm asked for the area between the curves and I'm not given limits of integration, it is implied that they actually intersect twice. Okay? Well, actually, if they don't intersect at all, obviously the area between the curves, we're going to need limits of integration, or we just say, well, I don't know, it's 0, whatever. So let's go ahead and set them equal to each other to find out where they meet. Well, the plus 3 and the plus 3, that winds up making things just a little bit easier. And we're going to go ahead and get 2x squared when I add x squared to both sides, minus 6x when I go ahead and subtract 2x from both sides. And if I pull out a 2x, I get x minus 3 is equal to 0. And that means x is equal to 0 and 3. My limits of integration are going to be 0 to 3. Now, obviously, if they meet twice, the downward-facing parabola is going to be on top. It's going to be more positive on this interval from 0 to 3. But to confirm it numerically, could I do the same thing on this interval that I did on the last one? Sure, pick a representative value. Take 1. And if I go ahead and evaluate f of 1, that's 1 minus 4 plus 3, and that's, what, 0? Okay. How about g of 1? Well, g of 1 is negative 1 plus 2 plus 3, and that's going to be 4. So we see that a representative value on this interval gives me a greater value for g of x. Okay. And so let's go ahead and put g of x in here first, and then subtract f of x. Okay. And from here, I can go ahead and simplify again. Let's go ahead and let's not be impatient. Let's go ahead and show the distribution of this one. Dx, the 3 and the minus 3 go bye-bye, and we're left with 0 to 3 of negative 2x squared plus 6x. And of course, that looks remarkably familiar. It looks like the negative of this intermediate step of finding the limits of integration. Interesting. So we have negative 2/3 x cubed plus 3x squared, and we're going to go from 0 to 3. Now, well, the great thing about having 0 as a limit of integration when you're dealing with a polynomial integral is you know that when you plug in 0, there's just nothing going to happen, right? So it winds up just plugging in the 3 is what's going to give us our value. And 3 cubed is, of course, 27, and this winds up being 9. So negative 2/3. What's 2/3 of 27? Well, it's 18. So that's negative 18 plus 27, or 9. Okay. Now these have worked out rather nicely. There are some that you're going to require your calculator for, and we'll get to a couple of those in the next video. But basically, this is how it's done. You basically just have to, if you're not given limits of integration, you find the limits of integration by finding out where the two graphs meet by setting them equal to each other. Once you've found those limits of integration, you just determine on that interval which one is greater and which one is less. You take the more positive one and subtract the more negative one from it, and integrate on the limits of integration, and solve. And that is pretty much it. We're going to do a couple that have a little bit of a wrinkle. We'll do a couple where like I let in, where there's an intersection in the midst of the limits of integration. Once we do that, we'll do a couple where we have to use our calculator in order to accomplish the integral, because there will be a couple that require us to actually do that. So of course, be on the lookout for that in the next video.